Here's another problem that involves a collision and conservation of energy. So putting them together. So read through this, press pause, takes as much time as you want, and then I press play. I think you can figure this one out a little bit more on your own because you just watched the previous example. It's very similar except there's one tiny little difference. So as you're working through this problem, think about what is different from the previous one because that's a really good way to understand the bigger picture when you compare two different problems and the way that you solve them, what's the same and what's different about them. So press pause and then press play when you want to go through it with me. Okay, I hope you realize the only difference is this is almost exactly the same problem as we just had. The only difference is that now the object that's waiting at the bottom to get to have the collision is also moving. Okay, so that's the only difference here. I'm going to have these same types of events. So the girl, the fairy kid, so they're fairies, that's why they have these tiny little masses. It just makes the math easier for us. Starts from rest at this high position. Then she is going to go down the half pipe at the very bottom. We're going to have an event right before the collision when she picks up her dog. And then we're going to have an event right after the collision, after she's picked up her dog. That's a perfectly inelastic collision because they're going to move together with the same speed after the collision. And then they're going to ride up the half pipe, and I want to know what's their new maximum height. So those are my events. I'm just like before, I'm going to get from this event to this event using conservation of energy. Then I'm going to get from this event to this event using conservation of momentum. And I'm going to get from this event to this event using conservation of energy. Okay. So initially, the girl at the top of the half pipe does not have any kinetic energy, but she does have potential energy. She has 147 joules of potential energy. That's her total mechanical energy because her kinetic energy is 0. And did I mess this up? Yes, I did. Okay, so right before the collision, this is when she's at the bottom of the half pipe. At this point, all of her energy is going to be kinetic energy. I don't know what her velocity is, though. I do know that her height down here is 0 meters, so that means she has 0 joules of potential energy. All of her energy is kinetic. And because energy is conserved from this event to this event, I know that this value here has to be equal to 147 joules. So that's what I've done here. And that lets me solve for her velocity. So the velocity of the kid, right before the collision, because that's event number 1. Okay. And now I'm going to try and figure out how much momentum she has, because that total initial momentum plus the momentum of the dog has to be conserved. Okay. You know, I did not include the kinetic energy of the dog here. I could have added in the kinetic energy of the dog because the dog is moving. But whatever I added in for the kinetic energy of the dog, 1/2 times the mass of the dog times the velocity of the dog squared, that would also have gotten added in here. And so both of these terms would have that extra kinetic energy, so the math wouldn't really matter. But when I consider the momentum before and after the collision, I definitely need to consider the dog's momentum because after the collision, the dog and the girl are moving together. So let's look at the total momentum of the system right before the collision. So this is my total momentum. It's going to be equal to the momentum of the kid plus the momentum of the dog. And the momentum of the kid is just the mass of the kid times the velocity of the kid. And that's the velocity the kid has right before the collision. That's what we just found. And this is the mass of the dog times the velocity of the dog that the dog has right before the collision. Now, the dog is running towards her at a speed of 1 meter per second. If I say that the girl's velocity is 9.9 meters per second, I'm making that a positive number. That's envisioning that the girl is traveling to the right. Now, the dog is traveling towards her. That means the dog is traveling to the left, so I have to make this negative here. And that's so important. Be very, 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 very careful that you make that negative because the two objects are moving towards each other. One of them has to have a negative velocity. So that gives me a total momentum before my collision of 27.7 kilogram meters per second. That momentum has to be conserved. That's also going to be the momentum I have after the collision. After the collision, the girl, the kid, and the dog are going to be moving as one object, so I add their masses together. And they're moving with one single velocity that is unknown. That's what I'm trying to solve for right in this event. So here I'm saying the momentum is conserved. So that means that that momentum I had before the collision of 27.7 kilograms per meter second, kilogram meters per second, has to be equal to their total mass times their velocity. And we get that they will have a velocity of 5.54 meters per second after the collision. That means that they have kinetic energy after the collision, and that kinetic energy is going to get transformed to potential energy as they rise up on the half pipe. So we can figure out how much kinetic energy they have after the collision. The two objects are traveling together as one mass, and this is the speed or the velocity we just found. So after the collision, they have 76.7 joules of kinetic energy. They have no mechanical energy because they're at the bottom there where we are saying we have y equals 0. So this is our total mechanical energy after the collision also. And again, notice that they have lost mechanical energy because of the inelastic collision. And now I can look at what happens at my maximum height. So my mechanical energy at that maximum height is going to be equal to the kinetic energy they have at the maximum height, which is just 0, plus the potential energy they have at the maximum height. And I'm treating their masses, again, as one single mass. And then I just need to say that this much energy is equal to this because of conservation of mechanical energy. This is like the Ki plus Ui equals Kf plus Uf. And I can solve for y3.